Chapter 6, Part 4, Meso compounds, Fischer projections, and stereoisomerism of cyclic compounds. So let's talk about how we identify all possible stereoisomers. So the number of stereoisomers possible for any molecule that has chiral carbons is 2 to the nth power, where n equals the number of chiral centers. Now be careful with your exponent math. I see a lot of issues with students here. If you have 2 chiral carbons, then you end up with up to potentially 4 stereoisomers. If you have 3 chiral carbons, that's 8 potential stereoisomers. I often see answers of like 6 or 9, so make sure that you're double checking your math there. Now, what if you have something quite large like cholesterol? Cholesterol has 1, 2, 3, 4, 5, 6, 7, 8 stereoisomers, chiral centers. That means that there are 2 to the 8th possible stereoisomers, which means 256 possible. Now, we could not possibly draw all of those out. It would take ages, and we're definitely not going to do that as part of a video. But let's do an example where we could do that. So 2,3-dibromopentane. We have 2 chiral carbons, which means we have 4 potential stereoisomers. Now, to start drawing your stereoisomers, you have to just pick one and draw it. So one possibility would be that both of the bromines are on wedges. Now, to draw the enantiomer of this molecule, I would create a pretend mirror plane. And I could either draw this molecule exactly like the mirror, where my bromine is now over here and on a wedge, or I can draw everything in the same order from left to right and flip-flop my dashes and wedges entirely. So these two are actually the same molecule, and anytime I draw the same molecule twice, I like to draw a box around it so you know that that's what I'm doing. This second molecule that I drew is just this one flipped over like a pancake. Now, these molecules also have diastereomers. So if we wanted to draw the diastereomer of this one, I didn't leave myself a lot of space, but I will try. I would just change one of the chiral carbons. So I'm going to leave this one on a wedge and switch this one to dashes. Now, this molecule is going to have an enantiomer as well. Let's draw it just like the mirror image. So that would be the enantiomer of that one. This happens to be a diastereomer of the one above. And then we also have another, let me add a different color, another diastereomeric relationship going across. So these are going to be diastereomers of each other, and these are diastereomers of each other. So we have quite a few relationships as we draw all of these stereoisomers out. We have diastereomers going in multiple directions. We have enantiomers going across. So what you'll notice is that any molecule can potentially have one enantiomer, as long as it doesn't have a mirror plane running through it. But that molecule will also have multiple diastereomers typically. So on this slide, we're going to look at 2,3-dibromobutane. On the previous slide, we had 2,3-dibromopentane. So I just want to point out the difference there. So 2,3-dibromopentane, butane. There's a bromine here and a bromine here. Now there is another way to look at this that might actually be more helpful for this specific problem, which is to put the bromines kind of on the same plane. Here, the potential mirror plane is much more obvious. So we're going to draw all of our potential isomers using that structure. So if you want to draw all of the potential stereoisomers of a molecule, you start by just making a decision. And my first decision is that both of my bromines will be on wedges. Now, Here's where I've created kind of a problem. If I wanted to make the mirror image of this molecule, I would get the same molecule back. So that's a problem. These are not different stereoisomers, and this is where we're going to end up addressing the concept of a meso compound. That comes up on the next slide. So there is no enantiomer of this particular stereoisomer, but there are still diastereomers. So if I take one of these chiral centers and I flip-flop it, then I get a diastereomeric relationship. Now this diastereomer does have an enantiomer. If I draw a mirror plane and I draw a mirror image of it, I end up with a molecule that is the mirror image and also non-superposable. So this is the enantiomer of this molecule. And this is also a diastereomer of our original. So this compound ends up only having 3 possible stereoisomers, even though we calculated that there would be up to 4. So meso compounds are really, really interesting compounds. All these terms that we've used so far, diastereomer, enantiomer, stereoisomer, that's talking about a relationship between 2 compounds. But a meso compound is a compound on its own that has the property of being meso. So this is not a relationship between 2 molecules. A meso compound contains chiral centers and has an internal plane of symmetry, which causes it to be a chiral itself. It does not have an enantiomer, but it will have diastereomers. A meso compound is not optically active. This is something we're going to talk about in the next video, but I'm just combining all of the meso information here. A good example of a meso compound is tartaric acid. Here we have these 2 chiral carbons. And just like 2,3-dibromobutane, you can see that there is this potential mirror plane running through the molecule. And again, just like 2,3-dibromobutane, the way that it's going to be easiest to analyze this is to draw them like so. So I'm going to shorthand the carboxylic acid as CO2H. Oops, that didn't come out cleanly. Let me try that again. I have oxygen. I have 2 of them. Okay, that's worse. Okay, and then CO2H. And I'm going to draw the oxygens going in the same direction. So this is the version of tartaric acid that would not have an enantiomer. This is the meso version of tartaric acid. So it has a mirror plane running right through the middle that prevents this molecule from being chiral and also prevents it from having an enantiomer. However, I would encourage you to try on your own drawing out the diastereomers of this molecule. You'll find that just like our previous example, while there are mathematically potentially 4 stereoisomers, you're only going to be able to come up with 3 because 2 of the molecules you'll draw will be the same. So there are a couple different ways of looking at a molecule, and we've actually seen one already. We just didn't give it a name, and that was the sawhorse formula. So when you take your carbons and you kind of put them in this shape, you're creating something that looks like a workbench or a sawhorse, and then you're putting the things that are coming off of it, the interesting things, at the angles. This allows you to analyze only the substituents. But this also sets us up for understanding the Fisher projection. So if you were to look at this from above, so here's your eyeball looking down, this is what you would see. You would see your methyl groups pointing down away from you. The bond between the 2 carbons would be here, and then everything else would be coming out at you. And the Fisher projection simplifies this by putting it all on these like little hatch crosses here, kind of like a railroad. And the Fisher projection requires you to understand that this geometry here is implied. So this bond is implied to be going down. This bond is implied to be going down. And all of these bonds are implied to be going up. It's something that you have to understand when you're looking at the Fisher projection. Now, you might be asking, why would I do this? Because it looks complicated. The Fisher projection allows us to simplify molecules that have many, many chiral centers. So you'll see these a lot when you're looking at sugars, for example, because they have so many chiral centers. So one more topic here is the stereoisomerism of cyclic compounds. Cyclic compounds can be interesting because they are often more likely to have a plane of symmetry. And so with cyclic compounds, you're more likely to come across meso compounds or even potentially just achiral compounds that are not meso because they simply don't have chiral carbons. So this first example is 1,2-dimethylcyclopentane. There are two potential chiral centers here because there are 4 unique things attached to each of those carbons, which means there are potentially 4 stereoisomers of this molecule. Now, 2 of them are drawn here. These are mirror images of each other. They are both trans isomers. They have the methyls going in opposite directions, and they are non-superposable. If you tried to put them on top of each other, what you'd find is that the wedged bond would go on top of the dashed one, and this dashed one would go on top of this wedged one. So you wouldn't actually get a fully lined up molecule. And this is showing you how if you rotated this or flipped it over like a pancake, you would see how those bonds don't match up. Now, if you were to draw the cis isomer and then attempt to draw the mirror image, you would find that the mirror image just matches the molecule you already have. This is an example of a meso compound. There is a plane of symmetry running right through this molecule, and that prevents it from being chiral and also from having an enantiomer, although it does have 2 diastereomers. This is an image of this. If you were looking at this from this way, basically, you would see the methyls pointing up and the hydrogens pointing down. And here it's really, really plain, that mirror image as well. So in some other examples, you can see how you may have chirality or not. In the organic 1 class, we often use chair conformations to show how the chair conformation can actually change the outcome of this. In 2330, we do not. So I'm going to scribble out these chair conformations real fast. I forgot to remove them before I started this recording. So in this class, we're going to keep it a little more simple. This molecule is not chiral because there's a plane of symmetry running right through the molecule. Same with this one. And yet these are diastereomers of each other, even though neither of these molecules are chiral according to our definitions. The outcome would be a little different if we just thought a little more about it, but we're not going to do that. So diastereomers, and neither of these can have a mirror image because they are not chiral. Okay. So we're going to continue going here. We have 2 chiral carbons. We do have a plane of symmetry running through this. So that's going to make this achiral and meso. So this is one where, excuse me, the chair conformations do actually pretty nicely support these images, so I'm going to leave them. But you can see that These are the two different trans isomers, and they are mirror images of each other, so these are going to be enantiomers. There is no plane of symmetry running through these molecules here. So they are chiral. However, if you look at the cis versions, these are just going to be the same molecule.